First day I have taught you the Faraday's law. If you have any confusion, you can ask me whether any contradictory thing I have told you, so that misconception has been developed. And also in transformer part also, I have taken a brief introduction of principle of operation of the transformer, which you have learned into the last semester. Although it was online mode, it is a very typical process for learning environment, because I will tell you something, whether you will take it or not, that depends solely on you. And if you like it, then you can take it. Otherwise, you can refuse it also. I don't have any option to judge you whether what actually learning process going on. That's if you are hungry, you can get it. Otherwise, it is a waste of time from both sides. However, at the end of the course, you have to learn something else, which you will have to deliver at the time of interview. And I don't think you, in the second year, you are so much worried about any job interview. But today, the trend is that people are moving from software to hardware section. I don't know what's the crisis is there, and the people prefer to have the job into the hardware section. And main problem of the hardware section, they have to face the technical interview, and the technical interview means in electrical engineering, you will see that mainly dominating with the machines, because this is a very good topic for the interviewer to get the technical judgment on you, so that you can perform something else. And I have learned many things from IIT and etc., the different institutions, that the basic machines which is normally discussed at any interview is primarily is the transformer. There are interviewer also feel comfortable to ask some question on that topic, and the candidate also supposed to have some good answer on that topic. And I can tell you feedback that there are several students from the this department who reported me after the interview that, sir, you have taught me the transformer and we have performed in the interview on that topic very well. Because even also some people are studying in abroad and some people are studying in the IIT and etc. They also give me some feedback that the way you have taught the transformer, so we have to face this equipment everywhere if you are into this hardware sector. And if you are in a software sector, that's a different issue. I don't know what they are doing there. So in the last class, now I will move to the class. In the last class, I have taught you how to develop the application of Faraday's law for a transformer, especially in a single phase transformer. As you know that you have learned the transformer in the previous semester on the virtual mode. So I don't know how much you have learned from that course, but even as I will have to go ahead with this topic, same topic, so I have to again impart some knowledge in the same topic to you. If you know it, then that's okay. take it easy because it is a background music. So that will be done today again. So again I am going for some presentation, and it is a, you can say that it is a repetition, but however, if any deficiency from your side for long form uh, learning process, so you can get it again from my lecture delivery. So you can today you can say that we are again remembering all these things for this in the transformer. One thing I can say that in a transformer, okay, let us go for the presentation then, so that present now. So today we will go for the discussion on the very important thing is that any device basically modeled on the circuit basis. You know that circuit, AC circuit you have studied. So that on that learning from the AC circuit you can solve the numericals. Numericals is required for designing a spec because you have to design a system for a particular voltage, current, etc. So you have to do some numericals. So for a single phase transformer, similarly a circuit is already developed in the first semester. So in second semester we are going ahead with that. So equivalent circuit of circuit for a single phase transformer. Okay. So I'll do the exact one. Okay. Exact one. What is the exact circuit? You have to remember exact circuit. Actually, the transformer model is basically placed by an ideal system. So this ideal means a primary and secondary winding without having any parameters. Only simple the voltage U1 and E2 will be there. And this is taken as the ideal one. Okay. So in ideal one, so what is the benefit of the ideal one? So this is called ideal. So ideal transformer benefit is that into this it maintains the transformation ratio. So N2 is to N2. You can write it here. So here, ideal one, U1 by E2 is equal to N1 by N2. Where this U1, you know that RMS value of the induced EMF, and the E2 is called the RMS value of the induced EMF for primary and secondary, and they have the terms N1 and N2 correspondingly. But you know the practical situation is different. Different means in a practical a winding a magnetizing current will be there. You know that in a practical situation induced EMF require a magnetizing current, and a core loss, that means equivalent to eddy current, and hysteresis loss also will be there. So you can say that this is a magnetizing branch reactance. This is called the core loss branch resistance. These are placed across the primary source voltage, across the primary voltage here. And also along with that, you know that some leakage reactance also will be there, that is called the X1. And along with that, some copper resistance of the primary winding also will be there. So that's actually the circuit of the primary winding. So, and if we apply a voltage V1 RMS values, that will be here. And the secondary also similarly, that will not have the magnetizing branch, only the resistance and leakage reactance of the secondary side will be there. It will be X2, the leakage reactance, which will be the copper resistance of secondary winding, and the R2. And then there will be a load, actually, load. This will be a load connected, if it's connected or not connected, whatever may be the load. So, and then across this there will be voltage of secondary winding, and also there will be a current into the secondary winding, that is called I2. So, anybody else? Any response whether this circuit is correct or not? Hello? 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 Hello?
Sir, it's okay. You are not given that current division in the primary branch.
No, that I have not shown here. Only the circuit I have drawn, whether this circuit is valid or not. So, as far as my knowledge is concerned, there are two circuits. Still, there are two circuits. One is primary, another is secondary, and they are distinctly isolated. Assume an ideal transformer, and the ideal transformer is shown in the box. Although it is a single-phase transformer, circuits for primary side and secondary side. Now we can apply the another thing, development. This circuit can be replaced by a single circuit. Okay. Do you know how to replace this circuit as a single one? How to combine these two circuits mathematically as a single one? So, what is that?
So by reflecting the resistances on one side.
So suppose we want to convert the secondary side to equal to. So actually you can see that here you see that. What is the target? Suppose from this equation, if we write down this, so that means Q1 is equal to N1 by N2 equal to Q2. So if the secondary voltage is multiplied by N1 by N2, then this voltage becomes exactly equal to E1. Okay. And another, you can say that if this is a current is called the I2 prime, you know that what is I2 prime, and the I2 prime is called the reflection of the current arising out of the secondary current into the primary side, into N1 must be equal to I2 into N2 in opposite sign. Okay. So we can say that it is a mode. That should be equal. So thereby we say that if the I2 prime is equal to basically N2 by N1, sorry, into I2. So this is the another expression. So now if we calibrate the secondary circuit with this multiplier, because suppose the I2 is multiplied by N2 by N1 and the E2 is multiplied by N1 N2, then a calibrated circuit of the secondary side is arising out. So we can redraw it again. The secondary side can be calibrated like this. You can draw the another color red. The secondary side can be multiplied as a like this. E2 into N1 by N2 and the I2 into N2 by N1. These are the multipliers for the current, and as well as X2 can be multiplied by the N1 by N2 square, you know that is also another product coming, and the 2 is multiplied by N1 by N2 square. Similarly, Z also multiplied by N1 by N2 square. Then this circuit is new circuit. Okay, this part is a new one with this multiplier. We are calibrating the secondary side with this multiplication of the secondary quantities, and so V2 also multiplied by the same V2 into N1 by N2. So thus we say that each quantity of the earlier secondary side is transformed to some other else, and then you can see that this voltage is basically exactly equal to this voltage. Okay. So as if this potential, that means the voltage of the new red circuit is, I have not drawn the red circuit, just value I have changed. You have to imagine that secondary circuit is not earlier one, it has been changed. So we can say that the secondary voltage E2 is no longer now E2, it is a E2 by multiplied by N1 by N2. So according to trans ratio, we see that this is basically exactly equal to E1. So in calibrated circuit of the secondary voltage is exactly equal to this primary voltage E1. And as if the polarity also same, as if you can assume that as if they are short circuited here, okay? As if they are short. Is there any problem if we consider mathematically these two circuits is same, so as a short? Is there any problem? If we consider when mathematically they are equal, so potential of the both sides are equal, their polarity are equal. Even not only that, even the current also, this current is basically flowing to the secondary circuit. So that is equal to I2. So that is also I2 into the so current, all things are parity with the parity of the primary side. So thereby you can say that the mathematically the circuit can be done by single one with the secondary side calibrated one, and this circuit, new circuit we can draw now. That is actually you can draw the secondary. Secondary is now we can draw. So this is the secondary side where it is a R2 prime is equal to R2 by N1 by N2 square, and it is a X2 prime is equal to X2 to N1 by N2 square, and this is the ZL prime. This is equal to ZL in 1 by M2 square. This is the secondary side, and the primary side is as it is, and we can omit this ideal section because mathematically these are not required at all now. So you can say that the circuit is like this. This is called the V1. This is called the equivalent circuit with respect to primary side. Do you know that? Hello.
Yes, sir.
So that's also another thing also you can do. The primary, similarly by logic you can transfer from primary to secondary also. So this is a exact equivalent circuit. Sometimes some approximation also we can do, that is called the another circuit also we can do. The approximate equivalent circuit, you know, that is a very approximation. So now this is the concept of the circuit. So this is called the secondary circuit, and we have to know the parameters concept because I have drawn this circuit only for understanding the value of the parameter. Now this circuit is sometimes approximated like this way. I draw that because this is very much used for other purpose also. So I have to draw this. So sometimes it is. So this is called the approximate circuit. It is called the XM. This is P1. This is a R1. This is X1. This is R2 prime. Okay, prime. This is X2 prime. This is ZL prime. Okay. So these are called the approximate equivalent circuit. Now you know this is the approximation. This is not exact. So any approximation will lead to some error, but this error is very small. However, its benefit is very large because you have to avoid a complication of the T circuit. You can see that in earlier one. In the earlier one you have seen the circuit is T circuit. That means there is a T form. One form is middle, another some parameters here, some parameter here. It's require a complicated circuit solving method. So the circuit solution becomes easier here. So that's why it is adopted and it is used, no problem. As the transformer is a high efficiency actually device, so the error is very small because if the efficiency remains almost same, if we use the circuit, approximate circuit instead of the exact one, then there is no problem for using that. So that's why these are well adopted and well used for circuit solution of the transformer. Now you have to know the value of the R1 and R2. So basically then we can say that this can be approximated as a two value. One is called R equivalent, that is called the R1 plus R2 prime, that is called the X equivalent, and that is called the X1 plus X2 prime. Now I want to discuss these parameters so that you can understand a transformer in respect of the applied voltage. Okay. Now we can say that one thing we can do that. So instead of load, suppose we can load here. So instead of the, suppose there is a switch. Okay. So we can do the switch here. Undo. So now, instead of loading, if we short here, okay, making a short, what is the problem? May I ask you, just give me some light on that. Somebody has shorted the secondary of a transformer. So what will happen?
So very high current will flow.
So that is our point, because I am going for this circuit especially to discuss the abnormal situation arising out in a transformer. Why the abnormal situation can arise in a transformer? Because without knowing the circuit, you cannot judge it. So now we have to investigate on these parameters. That means this parameter. Suppose the parameter here, or you see that. This is the parameter. Where is my pen? So this parameter is called the R1 and R2. What is this values? R1, R2. Basically, what is it is basically? What is that? We have to now go for that. What is basically it is? R1 or R2? Anybody else can respond me so that I can go ahead with that.
The copper resistances.
Copper resistance. Yeah. So you know that conductivity of the copper is very high. Okay. So thereby the conductivity of the copper is basically in the range of 10 to the power 7. Okay. 10 to the power 7 its conductivity. So resistivity will be very, very low. Okay. 1 by conductivity is called the resistivity. So resistivity is very, very low. And so the copper resistance is low resistance. Low resistance means what is the range of the low resistance? It is basically less than 1. This is less than 1 ohm. Very, very less than 1 ohm, we can say that. So this value basically in a circuit transformer, whatever may be the size of the transformer, okay, whatever may be the voltage, whatever may be the current rating of a transformer. So you know that the VA rating of a transformer will decide the size of the transformer. So voltage will give you the ampere will give you the cross section of the conductor. Cross section of conductor. So this ampere will give you the cross section of the conductor, and the voltage will give you the concept of what is the. Okay, we will go for that. Only the ampere. Ampere means volt ampere. Ampere will give the cross section of the conductor. So the cross section of the conductor of the copper will give, although there may be the large number of terms, but the copper resistance is normally very low. Okay, and there is the another part is called the X equivalent. We have to know that because I have already told you that this subject basically I am preparing on the basis of so that you can face the interview on the electrical engineering. And any electrical engineering interview is normally will deal the transformer. So you have to mind it And those who are interested, those who want to build up their career, so you can learn it now. So books will give you the idea, no problem. You can have everything in the books, but as I am doing, so you can learn it. So X equivalent is called the reactance of the primary and the reactance of the secondary. What is the quality of the reactance basically? Can you give me idea what is that? How this reactance is coming in into the
So leakage reactance.
leakage reactance. Okay, very good. So leakage reactance. So you know that what is leakage. So now I have to ask you why leakage is there basically. Can you I am doing for this again, I am telling you that it is from the interview point of view. So why leakage is whether anybody can avoid the leakage, anybody else? Suppose I want to the value of the x1 and x2 to be 0, whether it is feasible or not, you have to ask me. Now today we will go for the basic things. Whether somebody is asking that I want x1 also 0, x2 also 0, whether that's feasible or not. So some transformer company have you asked you that you provide me a transformer so that these two value must be 0, whether it is feasible or not. You can give me some light on that, whether you can do it or not. This is the interview question now face me, because interview question will be very critical.
So I think it will be not possible, because
So
for
it
the
will be-
completion of the magnetic circuit, actually it has two parts. Either it can flow through the iron core, which has low permeability, high permeability,
No,
or
low
it can
permeability. I don't
sorry,
know
low
low
permeability. Sorry.
Yeah.
Or some part has to complete
Sir,
through the
high
air.
permeability, na?
No, iron has low permeability. Sorry,
Sir,
high
low
permeability, low reluctance.
reluctance.
Sorry.
High permeability.
Uh,
So it can also complete its magnetic circuit through the air or or some emitting material that is there inside the core.
okay.
So if we want to make it 0, we must use a material with very high permeability, so that it will so the whole of the magnetic flux can complete through the core.
Okay. So what does it mean basically? You have to design a very high reluctance material across the winding, okay, around the iron. So whether that's feasible or not. Find it very high reluctance, very high reluctance, so that there will be a 0 flux through that. Can you design that? Whether this material is available or not. My
Sir,
question
it is very tough to confine the magnetic flux in a desired path.
No, that's different issue. I want to say that
Sir,
a material
hello.
you have to design, or you have to provide the around the core, around the iron core, around the winding, you can say that, so that no flux will go through that, because it's very high, or you can say that infinite reluctance through that. Can you design a material which can have the infinite reluctance?
Sir, I studied that superconductors has this property. This certain temperature.
No, superconductor can you can say that type 2
Meissner effect.
superconductor. Okay, so that will not allow any flux inside it. Okay.
So Meissner effect.
Okay, Meissner effect. Meissner effect, that superconductor will not allow the flux inside it. So that purpose is different. Okay. So that is a different purpose. But here
We cannot maintain that temperature inside that temperature.
No, that is not an
formation.
issue. Not only case for the temperature also. The superconductor is basically actually will not use any magnetic material. My question is there. It's a purely conductor material. Okay, you cannot use any magnetic material inside it, and so the purpose of the transformer will not be served by the superconductor, because magnetic material you cannot use there, because otherwise there will be no magnetism there. Okay. Another thing is that the superconductor also destroyed by the magnetism. Okay. So after some critical value of the magnetic field, it will be destroyed. So the vice versa also be true. So that's the different issue. Okay, forget about that. Come to the normal situation. In any normal situation, do have any material so that you can have x1 and x2 0.
So we can use manganese.
Huh?
Manganese.
Which material?
The manganese.
Manganese. I don't know.
Yes, sir.
Whether it is a metal or non-metal.
Metal.
Okay. Let us discuss on that, because this is very tricky question, so that you can have. You know that B is equal to mu H, okay? This is a very simple relation, you know that. And B is equal to flux by area, and the mu is equal to mu naught and mu r, and H is called the magnetizing field, okay? So that it will be, flux will be induced. But anyway, mu r, what will be the value of the mu r in normal range, okay? What is the value of the mu naught? Do know that it is 4 pi into 10 to the power minus 7 Henry per meter, okay? It is the value of the mu naught. And what will be the value of the mu r? Ranges of mu r, can you have any idea?
800 to
No, mu r can go from greater than 1, okay? At least value of the mu r is how much? What is the value of the mu r? If it is a ferromagnetic material, okay. If it is a diamagnetic, that is different issue. We are not discussing the diamagnetic material, okay. We are discussing the ferromagnetic material. So mu r is basically, okay. Any response?
So mu r will be 1 for air, no?
Yeah, 1 point something is air. So air, conductor, etc. all will be conductor also even. So mu r can take, the minimum value of mu r can take is equal to 1, okay. So in that case, the value of this is basically actually this is not equal to 0, okay. This is some finite value, okay. So when we are designing the reluctance, okay, so that will be the length of flux by 1 by mu naught into mu r into the area of the flux. You can say that mu r can go up to 1, but mu naught should have some value. It should not be 0. If it is a 0, then it can go for the infinite. But even the mu naught 0 is for the vacuum. Okay, mu naught value is for the vacuum. Even you can have no material. Suppose there is absence of material in space, free space. Suppose this is a free space. In that case, free space also you have a finite amount of reluctance. Okay. So in that case, you can say that reluctance cannot be made infinite. That is the main problem. It should have always some finite value. And that's why the reluctance around the MMF, any MMF, is always doing some finite value. So reluctance around the coil, primary winding, around the secondary winding. Suppose this is the reluctance of the, I am not drawing the actual circuit. Again, you can see that reluctance across this coil, so it is coming around the surrounding material except the iron. So this 2 bar is basically iron. So other material will be present that should not have any infinite reluctance. So thereby the flux, leakage flux can be 0. So leakage flux is that flux which is flowing except the iron. Okay, it's not flowing through the iron.
Sir, if we provide a good diamagnetic material, then we can also reduce the leakage reluctance. If we provide a good diamagnetic material around the coil. around the coil.
Diamagnetic material, name it. What is the name of the diamagnetic material?
For example, bismuth,
Bismuth.
or pyrolytic carbon.
Okay. So main problem is that you know that in a transformer, okay, we are discussing from the interview point of view. This is a voltage you have applied here, okay, across this. A voltage is applied. Suppose you have voltage 1 or 2 kilovolt, okay. So you should put a material so that this 2 kilovolt will be some insulation will be there. Otherwise, there will be a short circuit, okay, across this. So you should not use such material which can put the short circuit around the coil. So that's why main problem is that we cannot select the diamagnetic material also. So that's not a good insulating material. So you have to provide some insulating material there. So insulating material means the epoxy, resin, paper insulation, and various kind of insulation you have heard, oil, insulating oil. So those material are basically you have to provide. So those material will not have a infinite reluctance. Got it? Hello?
Yes, sir.
Huh? So it's not feasible basically. So that's why some leakage flux must be there. Although the leakage flux can be minimized. So one basic question is, so what we have to do? We have to do the leakage flux minimization. We have to do the, suppose this leakage flux, suppose I have drawn one leakage flux like this, okay? It is going through this, like this, this is called the leakage flux. So this is called the leakage flux, we say that. So I want to say that you have to minimize the leakage flux. Second question is, you cannot avoid the leakage flux that must be there. So that's why it's not a feasible here. Okay, it's not a feasible. This is not possible. Okay, this should not be 0. Always it should not be 0. So that's not feasible. But what we should do feasible is that you can minimize the leakage flux. So what should we do now? Can you tell me? Second aspect we are discussing for the transformer, because this is very much required for the understanding and the facing the interview. So now we have to minimize these reactance, X1 and X2. What should we do?
Sir, to minimize the leakage flux,
Yeah.
sir, we can wound the high voltage winding over the low voltage winding. That means the in the core type transformer we did that. Or we can use the sandwiched winding. This type of windings can reduce the leakage flux.
So this is one way for discussing. So now your question is very relevant, and you have answered right, but I don't know. As I am going for the class, so I have to repeat it. Your answer I am drawing basically. I am supporting you, and I have to explain the matter. So I am going for again the scheme, so that your answer is justified now. So this is a cross section, we can say that, of a transformer iron. Okay, I am not very good in drawing, but and also I am in hurry, so I am taking a drawing class, so don't mind. So you have told that the leakage flux is basically can be controlled by a placing a winding. Suppose this is a primary winding. Okay, this is a primary winding, and you have told that the if we do the winding on over it, one over it, or another. Suppose this is the primary one winding, or low voltage winding normally is placed inside it, and we are doing the another winding. Suppose this is the high voltage winding outside it. Okay, this is the high voltage winding. So we have told that the if we do this, then the leakage flux can be minimized. How it is minimized? Then you have to justify. So already in the last class, I have told you that here also you can justify that any current into the secondary, here I am drawing, try to understand what I am going for. So any current into secondary will be balanced by a counter current into the primary. Okay, that I have shown you. And you know that in a secondary, a current is leaving the potential coil. Okay, if the potential is this current is leaving it. So that means the direction of the current is like this. But whereas the reflection current into the primary, you see that it is entering to the potential. So in that sense, we can say that the current is always in opposite direction into the primary and secondary. Okay, am I right? Hello, got it? Or I can do it again. The direction of the secondary current and direction of the primary current are in opposite into the windings. Am I justified for that? Or from the equivalent circuit itself, I can discuss it from the equivalent circuit. Hello, what is the time? No, it's not so much high time, so you should be here. Hello, hello.
Yes, sir.
So can you justify the direction of the current of the primary and secondary for a transformer? What will be the direction of the current? So again I am going for that. From this circuit you see that if it is a secondary, then the induced EMF here, the polarity positive here. So current is leaving from this end. But whereas into the same reflection current is coming here, so it is a polarity is here, so current is entering to that direction. So we can say that the direction of the current of the secondary and reflection into the primary are in opposite. Can we say that?
Yes, sir.
Yeah. So this is a explanation from the circuit point of view. Basically that happens. Actually I have already told you that Lenz's law. Lenz's law I have explained so many times into the first class. So the induced EMF will be such that direction of the induced EMF I have explained to you. The direction of the induced EMF will be such that this opposite direction of the current will arise into the primary and secondary circuit. But that also is supporting the equivalent circuit also. Okay, so that is also supported by equivalent circuit also. No problem. You can understand from the both sides, from the Lenz's law as well as from the circuit itself. There should not be any contradictory things. So what I do that then if the current into the primary side is like this. Okay, this is the current into the primary winding. Primary winding. Okay. That current can be drawn into the black, so that you can understand black. So this is the current into the primary winding. Okay, current into the primary winding. This is the orientation of the I1. We can say that. So what will be the flux through leakage flux flowing for that? Can you draw the leakage flux for this? I have shown the current. It is a like this. What will be the leakage flux drawing for that? Can you draw the leakage flux?
Up.
Huh? Up. Yeah. So it will then go like this way. Okay. Am I right? Is it direction is correct?
Yes, sir.
Huh?
Yes, sir.
Huh? So this will be the leakage flux for the primary, or you can say that phi A leakage for 1. Okay. So phi leakage L for 1. Now, what will be the direction of the current for secondary?
Opposite.
Opposite. So that must be like this. So this will be the direction of the current through the secondary. So this should be the I2. Okay. So then what will be the flux for this, for the secondary? So secondary flux will be like this. Can we draw? Am I right? Phi L2. Am I right or wrong?
Yes, sir.
Secondary flux will be like this, leakage flux. So you see that. So here is the, we see that the so the leakage flux is confined into this zone. Okay, you see that leakage flux is confined into this zone. Okay, so if you make the low voltage winding and the high voltage winding as close as then leakage flux will increase or decrease?
Decrease.
Decrease. So this is the criteria so that you can minimize the reactance. Okay, so that's why transformer always prefer any winding 50% is one leg. Both of the primary and secondary must be on the 50% of the one leg. Another 50% will be here also. Okay. This will be further 50% of the both. So thus the transformer is designed and manufactured also so that the leakage flux is tackled. Okay. So that is the main design aspect or the minimization process of the leakage flux and the leakage reactance. So thus, one important thing we have discussed. So distribution of the winding for a single phase transformer, 50% one leg, 50% other leg, is a one possible solution to minimize the leakage reactance. This is the main. Okay. So we have discussed how to minimize the leakage reactance. So why leakage reactance minimization is required? So what is the problem? If we do have the large leakage reactance, so what will be the problem? In a transformer, you have studied the transformer.
To improve the voltage regulation.
It will impact the voltage regulation. You know that very well. So we can
also
write
power
the,
factor may be changed.
no, power factor decided by the impedance. Okay, here. Power factor always decided by this. What is the power factor? Power factor is basically B2 and the angle between the I2. So that I2. So power factor means it is the B2 and it is the angle is I2. So this is called the phi is called the power factor angle. Here angle. Here angle. So it is not dependent on the transformer. It's not dependent on the transformer as all. It is a solely dependent property of the load. Okay. Do you have any confusion on that? Power factor is decided by the load itself. It's not a property of the transformer. Okay. It's outside of the transformer. Okay. So the what was the topic? Okay, just a minute. What was the topic? Voltage regulation. So voltage regulation or VR, you can say that it is equal to the I into I2 R2 cosine of phi plus minus I2 X2 sine of phi by V2. Okay, this is the voltage regulation formula. So if the oh no, it is the R2 not R equivalent. Okay, it is the X equivalent. So this is the voltage regulation formula. So we can say that the X equivalent, I equivalent. So X equivalent is normally very greater than R equivalent. Normally in a transformer, X equivalent is very greater than R equivalent. So voltage regulation is mainly decided by the X or the leakage reactance. So that's why low voltage regulation require low reactance. Okay. So sometimes the voltage regulation is represented by per unit voltage regulation. You know that. What is the per unit voltage regulation? Suppose 0.1 per unit voltage regulation. What does it mean? Do you know that? What does it mean? We don't know. Okay. No problem. Now another thing we have to discuss. So sometimes leakage reactance is deliberately, suppose it is a, now we are going for the question, what we have started. So if there is a short circuit here, okay, instead of load, and you know that these values are very small, okay, already we have designed very small value of the X and X2, and the R1, R2 naturally are small. So if we by mistake apply the rated voltage, suppose by mistake somebody has applied a rated voltage under the short circuit, what will be the case? What will be the case? Do know that very large current will flow, okay? Large current will flow through the spark, okay? And this current is not naturally is beyond that rated value, okay? So rated value, more than the rated value current will flow and the transformer will burn, okay? So any short circuit is dangerous for the transformer. It will burn the winding, okay? Because the current will be flowing more than, and sometimes you found that in the news that a transformer has burned or catch fire into the transformer. So the catching of the fire into the transformer mainly due to the short circuit. Sometimes you know that. So short circuit is very dangerous for a transformer. So always you have to be cautious about that, whether there are any short circuit or not. Although no load is not a dangerous, you can have the no load condition. So there is no load. Suppose you don't have any load, it is an open circuit, okay? So there is no problem. You can energize the transformer. So there will be no problem. Because why? No load is not a problem in a transformer. Why? Because this current then is zero, okay? There is no current into this path, and only current is this. This is the only current flowing through this. It is called the no load current. Can you say whether this no load current is small or large? Do you have any idea what is the percent of the no load current normally flows
It's a
in terms of 3 to 5% of rated current. Okay, 3 to 5% of the rated current. So that's why we can say that very small current will be flowing through this. So the that's why if 3 to 5% when you apply the rated voltage, okay. So at the rated voltage, if you apply, then the current is so magnetizing current also small, and this current is very small. So that's why no load energization is not a problem, but short circuit energization is a problem. It will burn because very large current is flowing through the transformer. So that is a problem into the power transformer. You know that what is the power transformer? There are two types of mainly transformer we can see. One is called distribution transformer, another is power transformer. What is the meaning of these two? If you have any idea, you can ask me. What is the difference between the distribution transformer and the power transformer? This is a relevant question. Every interviewer will ask you what is the difference between the distribution transformer and the power transformer. Hello. Can you shed a light on that? So what is the difference basically?
So power transformer
Yeah.
merely operated on full load condition,
And
and distributed transformer operated half full load, 50% load of.
may not be. Okay. So that's not a criteria. Actually, distribution transformer always used at the end. Okay, there is no further transformer beyond the distribution transformer. Distribution transformer is normally used normally near to your distribution point. Suppose you are using the electricity in your room, so that's coming from a distribution transformer. So some industry is using some higher voltage also. Suppose the 3.3 kilovolt also for some the machines, etc. So that is also coming from a distribution transformer. So distribution transformer is the last transformer where you use, and solely this transformer size is very small because it is a catering a power for a very small domain or region. So that's why the size of the distribution transformer is small. What does it mean, size of transformer distribution is small? That means the VA rating is small. So in a distribution transformer, mainly the voltage and current rating is small. This is the main criteria of a distribution transformer. That means voltage rating and the current both are small in comparison to power transformer. Whereas power transformer is largely used into the transmission line. Okay, various stages, you know that from the generation point of view. So from the thermal power station, there is a generation of the voltages, and from that low voltages, it will be transmitted through the transmission line. So it is boosted up by the various cascading transformers. Those transformers are called the power transformers. Similarly, after transmission, it is coming down again for the utilization at the distribution transformer. So that's why there are several transformers are used. So those transformers are mainly called the power transformers. Those transformers mainly stay into the substation. So huge capacity. Their transformer capacity, VA rating is huge. You know that VA rating. So even suppose a 1 megawatt. What is the capacity of a 1 unit of the suppose Kolaghat power station. So 1 unit is producing around 240 megawatt power. Okay, 1
স্যার
unit.
স্যার
হ্যাঁ,
আমাদের 8:15 থেকে একটা ক্লাস আছে।
ওহো, তাহলে কি এখানে ছেড়ে দিচ্ছি?
হ্যাঁ স্যার।
কার কে নেবে?
DSD sir.
ও ঠিক আছে। তাহলে ওকে, আমরা পরের দিন 3 ফেজ ট্রান্সফরমার চলে যাব। আজকে এই সমস্ত পয়েন্টগুলো ডিসকাশন হলো। এগুলো তোমাদের আমাদের কি বলে আমার লাগবে পরে, শর্ট সার্কিটটা পরে লাগবে। ঠিক আছে।